Hey programmers, welcome back to day 8 of the Advent of Code. So let's jump into today's problem. So the input file for today is pretty interesting. It basically represents some instructions that we need to run on some type of computer. The premise of this problem is we're going to have to track some accumulator. It's really just going to be some number that starts at 0. We have 3 different instruction types, and notice that every instruction can also be accompanied with some number value. So let's talk about our first instruction type, which would be our NOP. So notice that in the NOP instruction, it also can take in the value. However, we don't really use the value. We just want to move to the next line. So the NOP instruction really just has us do nothing except go sequentially to the very next line in the instruction list. If we talk about the ACK instruction, what I should do is add the value in that instruction line to the current accumulator, as well as move to the next line sequentially. And finally, we have our jump instruction, which also takes in a value, and we should just move to the line exactly val positions away. So that means if our value is a negative number, we jump back that many spaces. If our val is a positive number, then we jump ahead that many spaces. And with these 3 different instruction types, we have a way to actually run an algorithm through this instruction list. We always start at the very first instruction of the list. That means this one at the top. And we also begin our accumulator with the value of 0. They tell us in part 1 of the problem that if we actually evaluate the instruction list, we're going to end up in a cycle. So to make sure we don't get trapped in an infinite loop, I'm just going to mark off the lines that I visit. So initially I start at the very first line, and I'm also going to mark it as visited. Since this is a NOP instruction, I don't really do anything except move to the next line sequentially. I'm also going to mark this one as visited. But if I evaluate my instruction, it says ACK plus 1, so that means I add 1 to my accumulator. So now my global accumulator has a value of 1. Also remember that for our ACK instructions, not only should we modify the accumulator, but afterwards we should just proceed sequentially to the next line. So I move to this new instruction of jump plus 4. I'm going to be sure to mark it as visited. Since this is a jump instruction, I don't modify my accumulator, but I should move exactly 4 lines down my instruction list. So that brings me all the way down here. This one says ACK plus 1, so I should increase my accumulator by 1. And now I can move down to the next line sequentially. I have a jump minus 4, so I don't modify my accumulator, but I jump back 4 lines. Now I'm at ACK plus 3, so I increase my accumulator by 5. At this point I move down 1 instruction, and here I have a jump minus 3. If we jump backwards 3 instructions, we end up at this line, which we actually were at previously. Notice how I have it marked off. So what we want to do here is stop evaluating our algorithm. In particular, we know that if we continued, we would just get into an infinite loop. So I end my algorithm here, and I recognize that, hey, I've been at this line before. And so we stop our algorithm, and we should just end up returning our final accumulator, which happens to be 5 in this instance. And so I think that this algorithm is relatively simple to kind of implement out the gate. You could solve this in a few different ways. I'll choose to tackle this one recursively. So let's hop to it. All right, so here's the input file for today. It contains many different instructions. Let's go ahead and start by just parsing the information out of each of these lines. So I have my very classic read lines function. That should just give me an array of the strings for every line. So let's just see what that looks like. Console.log lines. So we'll run part 1. So I have all of those strings. Let me maybe turn each of these into an object where I have the actual instruction type as well as the number value that I need to use with that instruction type. So I'll go ahead and create a function for this. I'll call it, I don't know, parse instruction. And it's going to take in just some string and just return a nice formatted object. So maybe I'll start by splitting the string. So I'll do string.split. And if I split on a space, I see a space is what separates the instruction type from its number, right? So if I split on a space, that gives me 2 pieces of information. I'll call it the type, as well as the, we'll say, value. Nice. One thing I want to be sure to do is when I return an object, the type can be exactly what it is. It's just going to be some string data. But the value, I want to make sure that it's a number, right? So what I should do is say val points to the number cast of val. Otherwise, I'd have string information in this val field, which I don't want. In the long run, I know I have to do arithmetic with these values, right? So with that, now I can use this function. I'll go ahead and say const instructions equals, And I'll go ahead and just map over my lines, right? So lines.map, and I'll parse every instruction. So let's see what that looks like. I'll do a console.log on instructions. Probably going to be a huge array of objects. See what that looks like. And there I have my nice array of objects. And this is going to be more convenient to do some nice logic on. Maybe I'll even do a console.table here. So it looks like we have about 600 lines of instructions, which I think, for this part one shouldn't be too much of a big deal, because we just want to eventually get to the point where we hit like a cycle in our instructions. So let's create a function to actually evaluate the code. So I'm going to create a function. I'll call it, I don't know, get accumulator. And it's going to, of course, give me back the final accumulator. Remember that the premise of the problem is we want to run the instructions starting from the very first one until we get to an instruction that we ran before. And at that point, we should just return what our current accumulator is, right? So for this function, it's going to be recursive, I think. And we'll go ahead and take in the instructions array. So that shouldn't really change over time, but we definitely need access to it. And I also need to know my current instruction that I'm evaluating. So I'll just say that's a number. So it'll begin at 0, maybe just a nice default argument. Nice. And I think with that, for now, this should be okay. I think we'll probably have to add some more information here to make sure we don't get trapped in a cycle, but I think we'll cross that bridge when we get to it. So let's hop into our code. So based on our current instruction, so to get my current instruction, I should do instructions at index I. So I'm going to grab my current instruction. So that would be an object like this. Let me destructure out of it the type and its value. So I'll do const. So for this particular instruction that I'm at, I'm going to grab its type as well as its value. And then from there, I'll start by just checking the type. Remember that there are 3 different types, right? I have my jumps, I have my acts, and then I have my no operations. Just a 3-way conditional for these. So I'll check if my type is of jump, then I need to do that jumping logic. And the jumping logic is really just to move exactly val instructions away. And of course, if it's a negative, then I go backwards. If it's positive, then I go forwards. So if I want to just jump ahead, then I should just call recursively get accumulator with the same instructions array. That never changes. And I just need to manipulate I, right? The value I represents the current instruction that I'm at. And so if I want to use this jump operation, for example, if I look at like this one, this is saying that you should jump backwards 371 instructions, which to me is just about adding this value into my current I. So it should be as simple as I plus this value will perform that jump. Right? If it's positive, I jump to a lower instruction or a one below in my list. And if it's negative, then I jump to a previous instruction above. So that's looking pretty good. I'm probably going to have to do something with the return values for this, but for now, I'll just kind of lay this recursive case out here. Then let me do an else if, right? Else if maybe I have my accumulator instruction. So if type equals acc. So here's an interesting scenario. If the type is accumulator, then I know in the context of moving to a next instruction, they always tell us to simply go to the very next one sequentially. So it's just a +1 here. So for example, imagine I was at this particular instruction. If you see what I'm highlighting on the right-hand terminal. After I add 9 into my current accumulator, I will definitely just have to evaluate the very next instruction. So that's just going to be instruction +1 or I +1 over here. However, how can I establish the logic that I'm adding the value into the accumulator? So I'm trying to think about this code recursively, right? And so let's say that line 24 returns back to me the accumulator if I had to start evaluating things at instruction I +1. Well, if it gives me back a number accumulator, then my answer should just be my value plus what my recursive call gives back, right? So I'm going to assume that my getAcc function always returns a number representing the accumulator once I hit the loop, right? And so I'm going to return over here as well. I'm going to return here. And now for our no operation, that one's pretty straightforward. I think I'll just handle this within like an else statement. And the no operation just means go to the next instruction, and that's it. So it's basically going to be the same as this one, except I don't change my accumulator, so I don't need to incorporate the value at all. Just proceed to the very next instruction, right? Let's go ahead and add the logic now to make sure that we don't get stuck in a loop. In the part 1 description, they tell you for a fact that, hey, there is going to be a loop inside of the instruction list. And so we want to be sure to guard against that. A quick way to do that is just to track where I've been previously. In other words, what I's have I hit before, right? What instructions have I run? And so I can just add an additional argument here. I'll call it visited, and I'll begin it as a new JavaScript set. A set's great here because it has a very fast lookup time, right? Lookup for members in a set is going to be O of 1 because it's a hashed data structure. Cool. So I can start working in, I think, a proper base case. So I'll say, hey, if my current I is inside of visited, in other words, if I've seen this instruction before, then I have a base case, right? So what I'll say is if visited.hasI. So I'm just checking if I is an item within my visited set. And if it is, then what I should do is return some value. I think the move here is going to be to return a number, right? Something I always have to be aware of in my recursion is that I need consistent data type, right? So over here, especially in my code, I'm assuming that getAc returns a number. If it returns a number here, then it should always return a number. And I think the base number I want to return is 0, right? In other words, if I'm already at the end of sort of my chain of instructions, I'll return a 0 because I know as that returns up the stack, I'd be adding all of these values into that 0. And finally returning some full and probably a large number of the accumulator. So that looks good. So if I end up at an instruction that I've seen before, just return 0. And then I think with that, I just need to make sure that I add I into the visited set, right? So let's say that I is not in visited. Then I can go ahead and just run this instruction, no problem. But I should mark it as visited, right? Before I do anything else. So I'll say visited.add. I'm going to add instruction I. Cool. Remember that I is just like the index of the instruction, we'll say. So this is looking pretty good. I think let's start to give this a run. So I'm going to call getAccumulator, and I just need to pass in the instructions because I already have those nice defaulted arguments. But before I forget, critical things here. I want to be sure that all of my recursive calls, like over here in my conditionals, they should all be referencing the same visited set, right? And so I need to kind of share that information so I can just pass that along. Visited, right? Every recursive call needs to know, where we've explored previously. So this should be just good to go. You could probably use something like a global object as well. I'm not really a fan of that, so I just like to pass things in as arguments because I know that JavaScript is like pass by reference when it comes to our composite data types like sets, right? And so getAc should return a number. Let me just return this number. So I already have the expected output below. It should be 1,489. So let's run this, and we should definitely not get an infinite loop. That would be very bad. So give this a go, part 1. Nice, and there we have our solution for part 1. Nothing much to this problem. Could probably also figure out a nice iterative solution for this, maybe just using a while loop. But I think any solution you come up with has to have some analog for tracking some visited instructions. So for me, that was just a matter of using a JavaScript set. Cool. So at this point, I think we should just hop right into part 2. Part 2 is pretty interesting. Let's just hop into the platform. So in part 2 of day 8, what they tell us is, all right, you were able to figure out, what the accumulator is once you hit the start of that loop. But now they want us to actually fix the loop. In other words, they tell us that exactly one instruction is miswritten. They say somewhere in the program, there's a jump that should be a no-op or a no-op that should be a jump. That being said, none of the accumulator or ACK instructions were actually modified. So this should just be a matter of us locating exactly one jump or nop and flipping it right to the other one. Here they give us some examples. And what they're saying is if you actually were to figure out exactly which nop or jump you should flip, then your program will terminate, and so it won't get stuck in an infinite loop, and you'll end up sort of right after the last instruction. In other words, let's say that my total instruction list was 5. Your algorithm ends when you hit instruction 6, we'll say. You're basically just off by 1 at the very end. And they want us to just return the value of the accumulator after our program terminates in that way. I'm going to start by just copy and pasting my part 1 into this part 2 file. But we definitely need to adjust it. So I think code that can stay is definitely how we read the lines as well as parse out the type and value for each line. But we definitely need to work on our getAc function. And so we know that we need to sort of establish this logic where we kind of flip on a jump or a nop. However, I should only do that once, right? So that's going to be really the key insight. They also tell us that the ACK instruction doesn't change, so we shouldn't really have to do anything with that instance. Why don't I just do some cleanup in terms of that? In other words, I think it would be a little better if I can turn this ACK conditional into the else statement. So if I sort of just flip things around here, so I'll make this specifically be the else case, and then this one up top in the else if should be the nop case. Right, so this else statement now is implicitly going to be the ACK. So if I run this, I should get the same answer as before. So I'm going to run part 2. I want to make sure I didn't break anything. Right, so still 1489, but at least now we kind of have isolated and targeted the jump and the nop instructions. So let's start to refactor our base cases. So this base case right now checks, hey, if I get into a cycle, just return 0. And I don't want to do that anymore because now if I get into a cycle, I know that's just an invalid path and I don't need to actually do anything with that value. I kind of just want to ignore it. I think instead of using this scenario as returning 0, what I should do is have the scenario that they said in the prompt. In other words, when your algorithm is truly done, your value of I, your I counter, should be right after the last instruction. So to me, I'm going to change this and say, hey, if I is equal to instructions.length. Recall that the last element of an array has index length -1. So this tells me that I is just after that last instruction. Cool. So now this is going to be my affirmative base case, meaning I found the exact way to correct my code, correct my instructions, as well as return a valid accumulator. But now I need to also handle the visited logic, right? So I still need to check if I have a loop and make sure that that result doesn't bubble up to the top. And so the way I'll kind of handle that is I'm just going to go ahead and check if, let's say, like before maybe, if visited has I. So if visited has I visited it before, and I know that that did not work out well, right? So I'm going to return some value. I'm going to return, let's say, -infinity. And to me, I think this is just something that I kind of tend to do because it's technically going to be able to perform some math like the other number values, where I can still add and subtract things from -infinity, although it stays as -infinity. So at least it'll be compatible with my other number operations later on, right? And so I'll do that. And let's start to also give ourselves a way to actually flip an instruction, right? So I need to change a jump to a nop or a nop to a jump. And the important thing is I need to do that flip exactly once in my path, right? So I need to actually add that into my sort of recursive information. I think of like the recursive state of my code. So I'm going to start with, we'll say, flip available. And at the very start, available, that should be true, right? So at the very start, I have the ability to choose exactly one jump or nop to flip on. And so this is going to help me kind of determine that. So I'll be sure to now change these conditionals, right? So if I look at line 26, this tells me that, hey, I have a jump instruction, and I'm treating it like a regular jump instruction, right? But in some other scenario, it could be the case where I should treat this as a nop instruction. So if I treated it as a nop instruction, then I would need to run like this code, right? Notice how I just stole the code from the nop conditional. However, I can't be certain which one is going to work out, right? In all certainty, only one of these calls would give me back valid data. I know that the one that is invalid would get trapped in an infinite loop, so it would return -infinity. So let me use that logic to my advantage. So let's start to kind of repair this code. So a nice trick I can use here is, why don't I actually create a variable called paths? I know there are two sort of like branches I can take here. I can either just treat this like a normal jump. So I'll just move this up. So I could treat it like a normal jump, or I can flip it, right? And I also need to pass in the flip available, right? So I'm gonna keep flip available the same. So if right now it's true, then it stays true. If right now it's false, then it stays false. However, for this second call, if I want to actually perform the flip, I can only do that if I have a flip available. If I have a flip available, I should take the number or the quantity that this returns, and I'll also push it into paths. So I'll say paths.push whatever this returns. But I also need to be sure that I just flip available. So I just used it up, so I should set it to false now. That way down the chain later on, I don't flip something else. You could only flip one in a path, right? So it's looking pretty good. So this means that sometimes if I have a flip available, this paths array will contain two numbers, right? I just want to choose the number that is like not negative infinity. And so maybe a nice way to do that would just be to do return math.max of the paths array. I'm just spreading out that array because max takes in comma separated arguments, right? So I'm kind of using this math.max pattern as a way to just ignore and disregard the negative infinity. I know that any like valid number would definitely be bigger than negative infinity, right? So that's looking good. And I just want to write very symmetric logic for the NOP over here, right? So I'm going to do the same sort of paths array. So I'll say const paths over here. And I'll begin it as an array of that stuff. Maybe I'll style it like this. And now I need to check, if I have a flip available, right? So if I have a flip available, then I'll do the jump style, right? So I'll take this code, I think. And I'll go ahead and do paths.push. And I'll push in the result of doing the jump logic, right? So I want to actually paste this thing inside, sort of like this. So this code is a little nested, but at least it's symmetric in terms of jump and my no-op. And like before, I still want to return the path, right? The path that is definitely not negative infinity. So looking at this code, maybe I'll kind of space things out. It's getting a little crowded, right? Maybe this looks a tiny bit better. Looking at this code, I think we might be ready to test it. However, I should also, in my else statement, just pass along the same value for a flip available, right? So that should be good to go. And before I forget, for line 40, if I use my flip to turn a NOP into a jump, then I should need to set this to false, right? And also for line 37, I need to definitely pass in the plain old flip available. So I'm only setting flip available in my recursive call to false if it's true right now, and I'm actually using the flip. So something important to note about this code is we're basically trying every possible path. In other words, if I have the opportunity to actually flip a jump to a NOP or vice versa, then I'm going to take it and see if that works out. So we're trying all of these paths. And because we're trying multiple paths now, what we should do is give them technically separate visited sets, right? Because I know that these paths can actually hit different nodes as they kind of make their journey down our instruction list. So to accomplish that, I want to make sure that when I pass my visited, I create a copy of it. So the way I can do that is I can say const new visited. I'll say new visited equals a new set of the current visited. So if you pass a set into the set constructor, it just creates a copy of it, which is nice. And now over here, whenever I pass in visited, I really want to pass in my new visited, because I don't want things to get mutated across these different paths, right? So I'll say new visited. So a lot of code. I think at this point, we're ready to give this a shot. I do kind of agree that this is tough in terms of how we structure this code. Let's give it a go though. So I'll run part 2. Nice, and there I get 1539. So let's take a quick lay of the land here. So don't be intimidated by this code. Notice that the code we do in one of these if statements is just the same in the other one. Maybe you can find a way to clean up the code. But here's the overall logic, right? So if I kind of read like the story in this code, I have this very important base case. This base case tells me that I've successfully found the ending of my program. In other words, I hit an instruction that is just outside of my instruction list. So I know I found the winning path, and so I return 0. The reason I return 0 is I want to return this number all the way back up the stack, because occasionally in places where I've actually used an ACK instruction, I need that number to actually do some addition with the value at that stack frame, like at that ACK stack frame, right? Cool. And so along with that, I have this additional base case that tells me, hey, have you actually visited this instruction before? And if that's true, that means that I'm entering an infinite loop, right? If you travel through your instruction list and you end up at a position that you were previously in the same path, then you're only going to get trapped into an infinite loop. So I'm going to return negative infinity because I'm using negative infinity as sort of like a signaling value to say that, hey, this path did not work out. So you should effectively ignore it. And after that, let's say that visited does not contain I. In other words, I haven't used this instruction in this path yet. Then I'm definitely going to add that instruction to my visited set. That way I don't visit it later on in this path. And so to do that, I create a copy of the visited set. That way I can have each of these different recursive calls track separate paths, right? Nice. Then I just unpack, my instruction, no big deal there. And then I have my conditional logic to perform the correct recursive call depending on the type, right? So for type jump, I'm going to always treat it like a regular jump, right? So I just have my core logic here. But if I have a flip available, remember that we set that Boolean above. So if flip available is true, then I'm also going to try to treat it like a NOP. And when I treat it like a NOP, I need to make sure that I flip that Boolean to false. That way down this same path later on, I don't flip something else. You can only flip once in a path, right? I'm going to push both of those number results that I get back from my recursive calls into paths. That way when I take the math.max, any paths that did not work out, that is any negative infinities, are effectively ignored, right? Any valid number of accumulator would definitely be greater than negative infinity. And I just have the inverse logic for this no-op conditional. Finally, in this else statement, we do our plain old ACK instruction logic. In other words, I go to the next instruction, I keep flip available the same, but I am sure to add my value right now to the result of my recursive call. That has the effect of summing up all of these values in my path. So there we have part 2 of day 8 of the advent of code. So I do think that this problem is pretty tough. That being said, I still had quite a blast working on it. I do love recursion. That being said, I'll catch you tomorrow for day 9.